Now, math induction is really kind of an interesting concept here. It's a method of proof, okay? We were just talking about geometry proofs. It's a method of proof, but it's a totally different way of proving things than you might have done before, okay? When we're proving things, a lot of the time we'll start with certain given information, and then we'll logically go from there and try to prove whatever it is, okay? What we're doing in this situation is we're going to be looking at different relationships. A lot of the ones we're looking at are going to be dealing with sums, okay? And we're going to try to come up with some rules that generalize what certain sums will equal. And then as a result, we'll have to prove it, okay? One of the ones we're going to do today is the sum of the first so many odd integers. There's a nice formula for that, and we're going to prove that today using this idea. The reason why this is a little bit different is because it kind of uses the concept of a chain reaction. All right, let me kind of show this to you here. The best example I can think of a chain reaction is, let me just do this, is a domino. Okay, how many of you have played with dominoes before? Okay, I've never actually played dominoes where you're actually playing the game dominoes. I always just played with them where you set them up and you knock them over. Okay, so, whoop. What happened to that? Okay, I don't know why it keeps making it go from there. Let's do it this way. Okay, so here we have a domino, okay? And if I take that domino and, it is going to make me do it every time. Okay. Here's all my dominoes. They're all nice and set up. I'm going to make some a different color here. Okay. And you'll see why in a second. Okay. Now, what's the basic premise behind dominoes? Okay, I take a domino, I push it over, and what happens? This first one, what does just this first one do? It knocks over the second one, okay? It knocks over the second one. So we can all agree that when you push over the first domino, it's going to knock over the second one, right? Okay. What if I came anywhere down the line, let's say to this one, and I said for any random one, if I knock it, if I push it over, what's it going to do to the next domino? It's going to knock that one over. Okay, so consider the logic that we're using here. I am showing that for the first domino, if I push it over, it will knock over the second one. So I know it works that one time. Then I come down here to any random domino and I say, hey, if that one gets knocked over, it's going to knock over the next one. So using that logic, I now have a chain reaction. If I knock over the first one, it's going to knock over the second one. And if the second one knocks over, falls over, what's it going to do? It's going to knock over the third one. And if the third one falls over, it's going to knock over the fourth. So here's why we just took any generic one in the middle and we said, hey, if that one falls over, what's it going to do? It's going to knock over the next one. So since we know it works with the very first domino, and since we know that no matter what domino we're working with, it's going to knock over the next one if it falls, we now have this logical chain reaction that we've built. So we can now surmise that, assuming we set them all up correctly, if we push down the first one, that last one is going to get knocked down. Okay? So if we wanted to prove, hey, the last domino is going to get knocked over, we have to use this kind of logic. The first one's going to hit the second one, and anytime one is hit, it's going to knock over the next one. All right? That logic creates the chain reaction, and we've just proven that the last one will get knocked over. All right? That's, in essence, what math induction is. Okay? Let's take a look at kind of the process. Math induction is a method of proving mathematical relationships using this kind of a chain reaction. All right? So, the very first thing we have to do in this process is we have to show that the first domino is going to knock over the next one. Show that it works for the first one. So, mathematically speaking, we're dealing with proofs involving sequences here. Show that it works for that first term. Okay? Then what did we do? We went down the line and we just picked a random domino. And we said, hey, it's going to work for this one. Okay? So that's the next thing that we do in our process. We're going to just make a statement. We're going to say, because we did prove it works for one, we're going to say, suppose it works for some random term, a sub k. And then here's where the majority of the work comes in. The majority of the work is going to come in right here on step 3. You've got to prove that if it works for a sub k, it will automatically work for the next one, a sub k plus 1. All right? So, here's the idea. It works for a sub 1, and then you've got a sub 2, a sub 3, all the way up to a sub k, and then a sub k plus 1. If you can show it works for this, then you simply suppose it works for some random one. You then will prove that it will automatically work for the next one. Okay? And then, of course, as you would with any good proof, you make your concluding statement. Therefore, this is true. Okay? Now, this is where this method of proof is kind of nice. Because back in geometry, you always started with your given information. But after that, sometimes we were kind of at a loss. We weren't quite sure where to go from there. The nice thing about these kinds of proofs, you can use these same 4 steps every time. And even within those 4 steps, when you're doing them, a lot of the work is going to look very, very similar from proof to proof. Okay? So, let's actually take a look at an example of supposing we are mathematicians looking at a pattern and trying to develop a formula and then proving it using this. Okay? Did you have a question? Sure. So suppose we had this sequence of odd integers. Okay? We're going to try to come up with a formula that will give us the sum of the first n odd integers without having to use the sum of an arithmetic sequence. Because if we're doing the sum of an arithmetic sequence, I've got to know what a sub n is, right? So that's something I'd have to figure out. If I wanted the sum of the first 500 odd integers, I'd have to figure out what that 500th one is, because the formula is n times a sub 1 plus a sub n over 2. We're going to come up with a formula to where you won't actually have to know what that last one is. Okay? So let's, again, imagine that we are the mathematicians looking at this pattern. We say, okay, well, let's see if we can see a pattern here. So let's look at some partial sums. What's the first partial sum of this sequence?
1.
1, good. And how about the second partial sum? 4. And the third?
9.
And how about the fourth?
16.
Okay. Now, do you see any kind of a pattern? What does it look like, Ken?
Squares.
There's squares, okay? 1's a perfect square, 4's a perfect square, 9's a perfect square, 16's a perfect square. What are those squares of for each of those partial sums?
Whatever we're summing. Like S1, so it's 1, S2, so it's 4, S3, so it's 9.
Okay, and those 1, 2's, and 3's are what? They're n. Alright, so check this out. It appears as though S sub n,
Equals n squared.
which is also the sum from, let's say, I equals 1 to n of this sequence. Now this sequence is arithmetic. What's a sub n for this sequence?
1 plus. Oh wait, what's the leading?
What's our common difference?
2.
2, so it's 2n, and then what would the term coming before that first one be?
-1.
Negative 1. So 2n minus 1 is going to be our arithmetic sequence. Okay? So we're doing the sum from I equals 1 to n of 2i minus 1. Alright, and we're saying that that will equal n squared. Okay? Now, that appears to be the pattern. Okay? And I'll tell you that is the pattern. That is actually correct. So if I wanted the 500, the sum of the first 500 odd integers, I'd just have to do 500 squared. So I'd have 250,000. Okay? That's going to be the sum of the first 500 odd integers. Which is kind of cool. But let's prove it. Okay? Let's prove it. So the first thing that we do, okay, we're proving that S sub n is n squared. So the first thing that we need to do is show that it works when n equals 1. Okay? So S sub n, we already said, okay, we already said a sub n is 2n minus 1. And we already saw that S sub n is 1. Now, does 1 equal 1 squared?
Yeah.
Yes. Okay? Now, I know this seems kind of silly to write out, but this is a proof. So you should actually show that you're doing it. Alright? 1 squared equals 1. Therefore, it works. You want to put a check mark or something there. Okay? You don't have to put a check mark, but you need to show this work. Okay? S sub 1 does equal 1. 1 squared does equal 1. Therefore, those are equal. Alright? Now,
What did you just do? Like, what's 1 equals 1 squared equals 1?
what I did here was, first of all, I figured out what S sub n is. S sub 1 is just that first term, right?
Oh, so you have that proof. Like, you need to have that proof. Right?
Yeah, we have to show that it works one time. Okay? And then you also need to plug 1 into the other side of what it's supposed to equal and show that those come out to the same thing. Okay?
Yeah.
So now, the next part here is just a statement. Alright? It's a statement that S sub k, which is the sum from I equals 1 to k of the 2i minus 1, should equal what?
Okay, squared.
S sub k should equal k squared.
Sorry, I zoned out a little bit.
That's okay. S sub k should equal k squared. Now, this is where we're picking that random domino in the middle and saying, hey, it does work for something.
It looks too something.
So now what we have to prove is we've got to prove it works for the next one.
Mr. I have a question.
Mm-hmm.
Right next to your sigma on the state, what is that? Is it 2 sub 1?
Yeah, that's what I said.
Yeah, why is it 2 sub 1?
2i.
Oh, alright.
Sorry, 2i.
Okay, it's confusing me.
Yeah. We're trying to state the, this is our a sub n, but we use that index I because it's in the sigma notation. Okay? Good question though. So now that we know it works for 1, and we stated that it works for k, if we can show that it will always work for the next one, that creates that domino effect. Okay? Now, question. If I have s sub k plus 1, what is it supposed to end up equaling? What's our goal?
The quantity k plus 1 squared.
Yeah, it should end up being this, which it may be helpful to FOIL that. Okay, you may find that useful. What does this equal when you FOIL? When you multiply it out?
K squared plus 2k plus 1.
Okay, good. K squared plus 2k plus 1. So, when we're doing this stuff for part 3, we ought to end up with that. Okay? And it can be helpful to recognize that goal here at the beginning. Okay? So, let's actually do this. I'm going to start with my sigma notation. And by the way, step 3 is going to start the same way every time. Start with your sigma notation. We're going to do the sum from I equals 1 all the way to k plus 1 this time of 2i minus 1. Okay. And then we're going to start expanding this sum out.
So do we write all the terms?
We're not going to write all of them, but we need to write a couple of them at least. So, first of all, if I equals 1, we have 2 times 1 minus 1. And you don't need to simplify this at all. You'll see why in a second. Then we let I equal 2, so it's 2 times 2 minus 1. Then we let I equal 3, 2 times 3 minus 1. And then I'm going to put a little dot, dot, dot. And I'm going to skip all the way to k. Alright? So it's 2 times k minus 1. And then the last term will be 2 times k plus 1 minus 1. 2 times k plus 1 minus 1. Okay? So you're going to be doing this every time. This is one of those things that's going to be the same every time. Expand this out. And now, what do you see? Does anyone see something there?
Is it kind of like the thing
It's the pattern.
where you like add the first and the last or something like that?
No, it's not like the arithmetic.
So the k plus.
Okay.
Well, it does end up being 1, 3, 5, 9 all the way up, but we don't know how far up to go.
That like k plus 1 is literally like k plus 1, not just like the term after.
Well, in the value that you're adding, yeah. What is this? Everything except for that last term. What is that? It's what?
The geometric.
A sequence?
Yeah, well, actually a series because it's added, but
What do you see?
how many terms did I just kind of bracket together there?
4. Infinite? What?
K of them. What's the sum of the first K terms?
Squared.
We just said it up in step 2, right? That right there is S sub K. This is terms 1, 2, 3, all the way up to K. Alright? That's okay, that's normal. It's totally normal. Alright? So guess what we have here? We just have S sub K plus this last set of brackets here. 2 times K plus 1 minus 1. Okay? Now, as we already said, this is why the statement up here was so important. We already know what S sub K equals. We know S sub K is K squared. Whoops. S sub K is K squared. So, we now know it's K squared plus 2K plus 2 minus 1 if you distribute in there. And what does that end up equaling?
K squared plus 2. Oh, plus 1 plus 2.
Yeah. Which happens to factor into K plus 1 squared. Which, if you recall, that was our goal.
Yeah.
Wait, can you leave it there for a second?
Yes.
Okay. So, why'd you write S sub K instead of K? Oh, you did.
Okay. Yeah, that's the S sub K. Let me do this here. So once we got the S sub K, then the S sub K we replaced with the K squared.
Alright, so
Yes.
Alright, we'll pass those over, but like next, will you show us like a case where it doesn't work? Like,
No, we're not going to mess with ones that don't work.
It always works.
like,
Any ones that you're given will work, okay?
okay.
That would be a little mean. It would be realistic, but it would be a little mean at this point.
Alright.
I want you to learn the process, so.
Alright.
Alright, so does the whole process make sense here?
Yeah.
Once we've gotten here, by the way, don't forget the last step. Therefore, the sum from I equals 1 to n of 2i minus 1, the sum of the first n odd integers will always equal n squared. That's what we just proved. Okay? Alright, it's cool stuff. You got to work through it though.